Good morning, everyone. My name is TJ Alumbaugh. I am a developer at Continuum, and this talk is about building TaxBrain. So I think it's maybe one part a community story. Here's what this community is doing with the NumPy stack to do something good for society. One part kind of a recipe if you are interested in doing this kind of thing, kind of a numerical or a number crunching Python package and putting it on the web. I think this could serve as a recipe for how to do that. And then maybe one part advice of these are some problems that we encountered and here's how we worked around that. So here's what we're going to do today. I just want to walk you through the background of what are we trying to accomplish here, what's the motivation for this, talk a little bit about a Python package that we built that's called TaxCalc. It's a tax calculator. I'll talk briefly about how we use Numba in that package. Can I just see a show of hands, anyone who would consider yourself a Numba user or has used Numba before? Okay, so just a couple of people. And then I'll do a little bit of a demo about how we, and show you this application running live. And then I'll talk about some deployment issues, which are very challenging a lot of times when you want to do something like this. Some lessons that we learned from all that, and then show you where we hope to go in the future, and some acknowledgments to end off. So first, the background. So what is this all about? Well, this work is sponsored by the Open Source Policy Center, or OSPC. The OSPC is a community with the goal of making policy analysis more trustworthy, accessible, and innovative by harnessing open source methods. So all of the great benefits that all the people in this room have leveraged from the open source movement, this organization wants to apply that to the world of making policy, and in particular to making computational economic models open source. So what is the state of the world? Open source is sort of the de facto in the PyData world. What about other worlds? Well, one world is the world of policy. And it turns out that everyone in this room is very strongly affected by computational economic models. These are models that determine what's going to happen if you change tax rates. These are models where we predict healthcare spending. These are models that are going to predict Social Security spending. And those policies are affected by models and what we think is going to happen in the future, and those policies then come into law. So the kinds of questions, how should we spend the money that the government brings in, or how should we raise money? Who's going to win and who's going to lose? Who's going to gain? What's going to happen to the economy if you do various things? That current state of the world uses economic models that are proprietary software, and policymakers and the public don't have access. So this includes the people that do not have access to the source code are people like members of Congress, people who are presidential candidates. They have policies that are based on models where the source code is not accessible even to those folks. And this even includes the government paying for the development of models in code where the code stays proprietary and is not open source. So there's a lot of bad things that happen from that. It inhibits creative policy solutions, so we're not harnessing all the brains that we could be if we put the code up online. It limits participation, and that's bad for democracy. It's bad for the democratic process. It inhibits external review, so we can't have someone go and look and find, hey, there's a problem in your code, there's a bug, because we just don't have as many eyes, because it's a closed source solution. And so we might be missing out on an opportunity for a more optimum policy, and that's bad for our economy. So that's the motivation for what the OSPC organization is trying to do. They've asked Continuum to come alongside and help them achieve that goal. And so the first thing that we've built is a tax calculator. And so that's a Python package. It's called TaxCalc. It's an implementation of the federal income tax code. It's a full implementation of the tax code, which is of course a moving target, and that we have the tax code for various years. So from about 2013 to about 2024-ish, depending on inflation rates and, potential policy changes and things like that. But that's kind of the time window where we would say we are faithful to the federal income tax code law, the current tax law. So what is this kind of calculation? It's known as a microeconomic simulation or a micro simulation, and it answers very basic questions like this. It's a very straightforward calculation. What happens if we raise the capital gains tax? How much revenue do we expect to get, or lower it? Raise or lower the maximum taxable income for Social Security, or the highest tax rate. You want to tax the highest earners more. What do you expect to get from that? One of the main things would be how do you create a revenue neutral policy, right? So we want to incentivize some other behavior, so we're going to create a tax cut over here, but maybe we'll compensate for that by raising taxes in another area. So how do you make sure that's revenue neutral? Well, you need to use a model of some kind. So this is a very simple calculation. And the way that it works is you start with some sample tax returns that are hopefully representative of the real data set of all the tax returns that we get, and I'll explain more about that in a minute. You take the set of tax code parameters, that is, this is the current income tax rate for all these brackets and all these other host of parameters, and you put those two things together, and that's what we compute in tax calc, and then you end up with a revenue projection. This is how much revenue we believe we're going to get. So what is that sample set of data? Well, it turns out that there is this thing called the public use file, or the PUF. And the PUF is a licensed data set that is made available by the Statistics of Income Division of the IRS. So if you pay taxes in the United States, that's your tax dollars at work. And it's basically about 150,000 or so sample tax returns with these privacy-enhancing modifications. So in other words, they do certain things. There are certain people in the IRS that take real tax returns, modify them. So for example, if you looked closely enough, you might be able to discern who a particular tax return belongs to, maybe for some extremely high earner, something like that. So they make some changes to that to protect people's privacy. And then it's also weighted to be statistically similar to the full set of tax returns, which is about 120-ish million tax returns processed every year. So the way that works is that there's an extra column of data in this data set that is a weight. So for example, for one of the tax returns where the income level is maybe between 50 and 60,000, which is sort of a national, in the average mean income, maybe the weight for that record would be 300,000. That'll represent 300,000 individual tax returns or something. But for another return in the data set that is, maybe has 2 million adjusted gross income, that would be a weight of like 5 or 6 or something like that. So that way, in a weighted sense, we basically have about 120 million different tax returns. So how does the tax calculator perform, this policy analysis? Really, what would happen if we did your policy idea? What we do is the top is the chart we just showed. You take, now I'll just call it the PUF. With the default tax code parameters and apply tax calc to that, and out comes the standard, if we did nothing, here is what the revenue would be. The purple in the bottom is your user-specified tax code parameters, so we want to change the max taxable Social Security income or something like that, or lower the capital gains tax. And that result is the blue. A different revenue projection, and so your policy effect is the delta of that. And actually, we do this for 10 budget years, so really when you typically run this in practice, you would get 10 deltas, right? So now I'll just briefly talk about how we've applied Numba in this package. So if you are, I didn't get too many hands for using Numba, so Numba is a jitter or just-in-time compiler for compiling Python code. Excuse me. So the general idea is that a lot of people in this room probably use NumPy, and there are certain kinds of operations that are great with NumPy, and there are other kinds of operations with NumPy that are very challenging and result in code that doesn't look so great. So one of those would be, if you wanted to have an if statement, or a logical and or a logical or on an element-wise basis. You want to check that condition. And you do not want to do a for loop over a NumPy array in Python, because that completely kills all the performance you were getting by using NumPy. So therefore, you end up with code that looks like this, which is when OSPC came to our doors, they had a bunch of code that looked very similar to this. So I think you can kind of see all that, the NP logical or, NP wheres all over the place. And this is definitely a way of ensuring that you will never touch this code again after you get it working, because it's very ugly, right? And who wants to go and mess around with that, right? So we apply Numba by using the JIT decorator, which basically will compile this down to machine level code. Now, the thing that you don't see is the for loop. We abstracted that away in a different iteration of this code. But just to show you what the actual tax logic looks like, this is a very common scenario where there's all these variables in this input, and it's an if-else. If this status variable, for example, one of these variables represents marital status, and so your particular tax burden is going to change depending on your marital status, that kind of thing. And then some very simple arithmetic, and then do a calculation and then return the answer. So that's great, but wait, there's more. Numba can do a lot of really cool things, and I'm going to continue to put this Numba logo like this until the Numba team actually creates a logo, because it's been around for like 3 years now, and they literally have no logo. So I think we should all just do this until that will incentivize the behavior that we want, which is for them to create a Numba logo. But okay, so there's a common pattern here. Like I said, we have 150,000 rows of data. Every row has about 200 columns, right? So it's just a big table of data. And every single tax law looks exactly like the same thing. For every row in this data set, do a bunch of operations, expressions, on the elements of that row. So, B sub I, C sub I, et cetera, et cetera. It all looks exactly the same. So we want to take advantage of that and lower the burden for our domain experts who are going to be implementing this tax logic. And then the other part of it is, the complexity of this all lies in the number of variables. I just showed you basically what the math looks like. I mean, it's an if, else, and other. The problem is that a lot of these tax laws or a particular deduction or credit or whatever, it takes about 40 inputs, and then for various reasons we return maybe 5 or 10 of those arguments, and it's just a lot of typing. So what can we do there? Well, what we did was we created a custom decorator called iterate JIT that uses the standard JIT underneath the covers. And what that does is it does a few things. One is that it handles this boilerplate code of wrapping the functions, and we do that at import time. So we don't really see a performance hit from this. But what we do is we have some boilerplate code that says, okay, get this column out of this data frame and iterate over it, and then put the answer back or whatever. So I'll show you in the next slide more specifically what I'm talking about. But from the caller's perspective, all that you do when you call this function is give those two arguments that I showed in the picture before. The parameters, which is the current tax policy, whether that's the default or yours, and then the records, which is really the puff file. So the caller calls it like this, but the function actually looks like this. So all those arguments, in this case, like SSIND and Mars and E02500, those are just column names for data frames. And those columns exist somewhere in either in params or records. So what we do is we have some code that when the caller calls the function, we go and find the right column of that name, pull it out, and then we have a for loop that it's a very boilerplate for loop code that we construct at import time, at function declaration time, and then what's the function that's called in the inner for loop is what the user has written here, and basically we will do the sub i's for them so they don't have to do that. So all of this basically will pull data out of a data frame, do the for loop for you, and JIT it so that it is, runs at compile time speeds. But this is the only thing that you have to type is at iterate JIT. So that basically explains everything there. We JIT the resulting function that comes from the for loop, wrapping. Shuffles arguments in and out of the data frames, and it provides this implicit iteration is very much like a SAS environment, which I don't know if people are too familiar with SAS, but those are domain experts who are coding up a lot of this tax logic have a SAS background. So that implicit iteration provides a programming environment that's very comfortable for them and allows them to very quickly go from what's in their head of how this tax credit works to making code. So if that's useful for you, there's some links at the end to where our GitHub repos are, and maybe you can use that same idea. But not everyone's a coder, and we want people who are not coders to use TaxCalc and do their own policy microsimulation. And so that's where we're going to show you the TaxBrain, which is the web accessible version of this TaxCalc Python package on ospc.org. So I'll show you that right now. So it's at ospc.org. Definitely invite you to go check out the website and get going with this. If you go to www.ospc.org, please enter your email address in here, and you can register as a new user of the website, which will give you access to the web app. So you can just put your email address in here, and then you'll receive an email with a confirmation link. Click on the link, go to the website, and set up your password, and then you're good to go. And once you've logged in, you just click on the apps link here, which takes you to, actually I could probably just maximize that so you can see everything. Yeah, so this is TaxBrain, which is the web accessible version of TaxCalc. And how it works is basically all the different inputs that are possible to add in code, we just have a box for them. And it's pre-populated with the 2015 default values, right? We have little hover-overs that tell you, okay, this is, form 1040, line 42, et cetera, and all that kind of stuff. So if you wanted to, so for example, for 2015, the personal exemption is set at $4,000. So what you can do is change that. This is my policy change. I would like to change it to, starting in 2015, the new personal exemption number is $4,200. And this little flag here is basically to say, do I want that to be indexed with inflation? So the default is that it would increase with inflation rates, and we have a certain set inflation rates. But if you just wanted to have that as a flat 4,200 for the next 10 simulation years, you could do that. But we'll leave it as a default. And then you can go on to the next area. And so you can get all the way down here to capital gains tax, personal income tax. You could change the top personal income tax rate, right? So it's at 0.396. We could change that to something like that. And okay, and then keep going on down. When you're ready to go, you just hit show me the results, and it'll start doing the computation. So it does that delta of the standard tax law versus your change for 10 budget years. And then we will compute some basic statistics about that. There's some pandas stuff happening, and it should be done here in just a couple more seconds. But what we do is, so here we are. So you've got 10 budget years, right, starting in 2015 up to 2024. And just as a general summary, it shows that if you implemented that policy change, you would get like 13.6 extra dollars in your in the coffer, so to speak, for the government for the year 2015 and all the way up. And then we have a whole bunch of statistics and data that these policy analysts are very interested in. So this would be the difference between, so this is the delta, right, where we've broken it down by AGI decile, so adjusted gross income decile. So the highest earners are here, the lowest earners are there. So we just adjusted the top income tax bracket, so the people who are going to have tax increase are over in this area. But we also raised the exemptions, so people who had a tax cut are over in here. And so on. So now we have the delta, right, difference between base, and these are planned by just income bin, right? So just straight adjusted gross income bin, where this is in thousands of dollars. And then actual statistics on the two plans. So here's what the base plan does by AGI decile. Here's what your plan does. This is, let's see, oh, and then now we bin it by straight income buckets, and so on like that. So you can go through this, and you can do that for all 10 budget years. You can look around that. Typically, probably people are not going to look around on the website at all this stuff. They maybe want to run some statistics on that or something. So you can save the output as a CSV. Right? And then if you wanted to record what inputs you chose, the parameters that you chose, we would save those inputs as CSV. So that's pretty much how it works right now. And so please do go to www.ospc.org and register, and you can start playing around with the TaxBrain. So I'm going to try and get back into presenter view. Okay. So how does this all work? How did we put it together? It's a pretty standard web app in many ways. We use Django to host the website. Celery, can you raise your hand if you've heard of Celery? Okay, just a couple people. So it's a distributed computing system. So this is actually the system that's going to help us have a responsive website, but then we need to go and have it some tasks done to do the actual calculation. So we organize all that with Celery. And for us, one task is that one budget year delta. So each time someone comes and does a simulation, we have 10 tasks that need to be done for now. And Celery needs some kind of message brokering system, so we use Redis for that. So the first thing that we tried, can I just get a show of hands? Everyone who's familiar with Heroku as a basic, okay, so many people, so it's a platform as a service, so you just think AWS plus some extra features that are easy to turn on that maybe cost a little bit more than AWS. So we just said, well, let's just do everything with Heroku. Seems pretty easy. So with Heroku, when you want to add extra services, you need a thing called Heroku add-ons. So if you want a database, you use a Heroku database add-on. So we needed to use Redis. So for our choice, we used Redis Green, and that seemed to work great for us. And then with AWS, you have these EC2 instances, but in Heroku, they use this word dyno. Right? So we have one web dyno, which is their standard sort of generic dyno for hosting the Django portion of the app, and then we would spin up these additional dynos that were Celery worker dynos that would do our work, and they're connected through Redis. So the result of that was that it was not great. And the reason is because for the kind of workloads that we were doing, only the PX dynos, which are the most sort of high-performance dynos in the Heroku world, could really handle the work. And so if you have any kind of workload, and this is, I think it's very relevant for this audience, the kinds of workloads that this audience does is probably not going to work well with Heroku dynos. If you have a high memory watermark of some kind, or a very computationally intensive kind of workload, it's not. We found that the performance was not great. And also these PX dynos are very expensive, and they just didn't perform as well as some of the other options. So we said, okay, well, let's keep the good parts of Heroku. We like some parts of Heroku, but the workers, we're just going to farm that out to AWS. So we did that. And the architecture looks pretty much like this now, where we have some number of AWS worker nodes, and the Django application talks to those worker nodes through HTTP. So we basically have sort of tax calc as a web service, and we split the calculation over all the budget years, and then recombine the results when everything's done. So what do those worker nodes look like? Well, they pretty much look like this. We have Flask running so that we can have these web endpoints to start the work and get the results back. On the worker node itself, we have one process running Flask, right, so that it can be responsive as web requests come in, and then we run Celery again with Redis underneath, and then the tax calculator is on the node installed, ready to do the work. So it's a stateless API, kind of a RESTful kind of thing. But there's really only three endpoints, which is one, start the work, which is just post, and we have a start job. Is the ticket done yet? So as you saw, it was waiting there. The website is really just asking the nodes, is this particular budget year done? And it's at the beginning, it has 10 tasks to start and then 10 to find out when they're done. And then when the answer is yes, we do have the result, go ahead and give it to me, which we get a blob of JSON back, which is the sort of calculated and values, and then we assemble it all and then display it. This is all deployed with Salt and services running with systemd. On an Amazon box. And it's cheap enough now that we can have a surplus of these workers, and if some of them go down, we just round robin through available nodes for all the work that needs to be done. So if some of the nodes go down, it's going to take longer because they'll have to do one task and then get tasked with another one and that kind of thing. But it provides this graceful degradation of service. If you are interested in using Numba with the Celery system, I would really suggest that you make a little note here. If you think about how Celery workers work, they're a process that's sitting there saying, I'm ready for new work to come to me. And then a task comes to them, and they need to call your Numbaized function, right, to do that work. Well, it's a jitter, right? So what happens is a new task comes, and the default behavior of Celery is to actually execute your task in a separate forked process, right? So the worker is its own process, right? But then it forks a process to do your task, and that's so that if your task, for example, had a memory exception or did something terrible, you haven't killed the whole worker. So in a JIT kind of environment, you forked a process, and then it needs to JIT your code, do the work, and then give you the answer, and then that process goes away. The next time it gets a task, it forks a process, JITs the work, and does it, and so on and so on. So you are JITting every single time. So Celery has a workaround for this. You can use a threaded pool instead of, and so it will spawn a new thread instead of forking a process using the G-event library. So the way that you turn that on is with this, which I'm not sure you can see. Yeah. It's that at the bottom there, -p eventlet is the way to turn on that behavior. So just a little tip for that. So this is a very exciting announcement for us and for OSPC. All of the code that now runs ospc.org is public. And so all the JavaScript and the CSS and the Django templates and all this distributed text execution is available on GitHub now at this site. So if you have some front-end skills or you want to try out your front-end skills, please submit. We're actively seeking pull requests. So you get a free website today, everyone. So you didn't know that. So yeah, just talking a little bit about deployment, because the devil is always in the details of these things. I mean, that's great to throw up something on a website and now people can use it, but the issue is that this is an actively maintained and developed resource, right? So how do we put this up in a timely fashion and have the fact that people are going to be changing this asset, the tax calc package, and we want people to have access to that. To start off, just to reiterate, we do use Heroku for deployment. It's very nice, git push Heroku master. Push to deploy is kind of the Heroku mindset, and it's great. A few months ago, I found out that people were, trying to do, for example, I want to set up my machine learning system on Heroku. That's a great idea, and I want to use Python to do it. Well, all the forums are in the Heroku developer area were basically, hey, I'm having trouble compiling SciPy. Hey, I'm having trouble doing all this. Because the way that Heroku works is that it will detect, okay, you want to run a Django application. You want to run this Python code, and you have a requirements.txt. And so a build pack is the Heroku speak for these scripts that will launch your app. And that is the thing that's going to pip install everything that you have. So when you say pip install SciPy on these Heroku nodes, that's not going to work. It's going to invoke a compiler, and the linkage is not going to be right, and it's not going to be successful for you. So you can actually have it specify a custom build pack. And so the recommendation that I would have for you is to use Kenneth Wright's Conda build pack. Kenneth Wright's of request package. He works at Heroku, and he's put together this build pack that allows you to install Conda packages for if you have things like scikit-learn or SciPy or NL2K or really anything that has SciPy or NumPy at the base of it, pandas, something like that. This will allow you to Conda install the packages that have a binary dependency, and then you can also pip install your other packages. So that's kind of on the Heroku land. In deploying TaxBrain itself, like I said, this package changes very frequently. The other thing is that it was very important to our sponsor that anyone should be able to reproduce these results. If I go in and type and do what I just did on the TaxBrain, I need to be able to share that with people, and anyone needs to be able to reproduce it. And we have very simple policy for running the TaxBrain, which is that whatever you produce on TaxBrain should be easily reproducible on a local machine on any platform. We just want to say that we guarantee that that's going to work. So how do we do that? Well, step one is you want to have versioning done properly. So I would very, very strongly recommend that people use Versioneer for their versioning. Is anyone can just raise a hand if you use Versioneer? Okay, it's great. It's a total drop-in, I guess you might call it a drop-in module. It's simply a drop-in solution to your Python package that does awesome things with versioning. And the way that it works is that you use git tag to tag a particular release, right? And then the git archive command is what will enable the Versioneer magic. And you can just go look through the documentation there. But the bottom line is that you use git archive will then take that tagged repo and then produce a version package on your local machine. So now that this version package is ready to go, you want to produce packages so that anyone can install it. And for us, we want to support Mac, Windows, and Linux, and 32 and 64-bit on those last two. So we use conda build to build those packages and then upload the packages to anaconda.org, or formerly binstar.org. So that's a way of making the binary packages freely available to anyone who wants to use them. So for example, you could invoke this last command at the bottom here, conda install-c, use the OSPC channel on anaconda.org to download TaxCalc, and it will bring all the dependencies onto your machine as well. And then when at deployment time, because we have that custom build pack, we have the Heroku push will do a conda install of the latest version. So what we learned there is Heroku is very expensive for compute and memory intensive applications. Git tag plus Versioneer and conda build and anaconda.org really allows us to have a transparent cross-platform deployment with reproducible results and a public history of changes. I would very recommend, if you want to do this kind of operation, that you have this numerical work that you want to make available through the web, be aware that your users are not going to wait too long. You need to find a way to be responsive to the user idea of you interacting with your package through a browser. So you probably want to chop your work up in some kind of way that works well for a web service. So in other words, if you can partition your problem into smaller units and then assemble the answer when it's done, that might not be the least amount of computational work, but it'll scale a lot better. So what's coming up next for this project? We're deploying a new kind of model, a more involved macroeconomic model. Healthcare models, Social Security models. We want to have some visualizations, maybe with bokeh or something, and lots of things happening with the TaxCalc package and OSPC.org. If you see a help wanted label on an issue, you too can be a good guy and make things better. So please do give it a look. I just want to acknowledge Matt Jensen, who's here in the audience, who's our managing director of OSPC, and thank him for sponsoring all this work. So there's our GitHub repos. Please go check them out, and thanks a lot for listening.